So previously I introduced unit step functions and the notation I'm going to use throughout Laplace transforms that will involve unit step functions. So just for a recap, u alpha, which is u subscript alpha. So u alpha is either 0 or 1. It is 0 for the values of t between 0 and alpha, including 0 and not including alpha. And then the function has a value of 1 after alpha, including alpha. And so we had three examples we looked at. We had u0, u2, and u alpha for any generic value of alpha, as far as alpha is any non-negative integer, a non-negative real number. So let's continue from this point on. We will take the Laplace transform of some piecewise function. Let's suppose, for example number 1, that f of t is the following piecewise function. It is 0 for the values of t between 0 and 2, and it is t minus 2 for the values of t greater than or equal to 2. First of all, before I proceed on with the solution, let me graph this function. So again, I will have my f of t on the vertical axis and t on the horizontal axis. And let me also mark the break-off point, which is 2 between, so this is 2 is the break-off point between the two domains here, the first domain being between 0 and 2, and the other domain being greater than or equal to 2. And I'm arbitrarily going to mark 2 along the positive t-axis. So graphing the first function value, which is 0 between the values of 0 and 2 on the t-axis, it is simply going to look like a horizontal line, which will be open at 2 on the t-axis. And then if I look at t minus 2, which I'm going to graph in red, so t minus 2, it starts at a value of t equals 2. So at t equals 2, the value of t minus 2 is 0. So it fills in the open circle on the blue function being 0. And after that point, we can graph the line with a slope of positive 1 and a y-intercept of negative 2. Then if I graph a line with a slope of positive 1 for all the values of t greater than or equal to 2, I get this red line. So here is the graph of f of t. As you can see, f of t is continuous on the domain 0 to infinity. So let's attempt to take its Laplace transform, but first we have to write f of t using unit step functions. A good way to write any piecewise function using unit step functions is to treat the function pieces as signals. So you can treat 0 and t minus 2 as two different signals. And you can imagine the right and the left endpoints of the domains associated with each of those pieces as the points where the signal turns on and turns off. So basically the left endpoint of a domain would be the point where the signal is turned on. Likewise, the right endpoint of that particular domain is where the signal is turned off. So to start off with this function, f of t. Now, Although 0 is a trivial case, let us still go ahead and write 0 using unit step functions. So the function is 0 on the domain 0 to 2. So that means we start off with a 0, and I'm going to attach u0 with it. So u0 signifies where this function starts. Likewise, this 0, the signal of 0, it stops at t equals 2. So I'm going to attach a u2 along with it. However, because the signal of 0 stops at 2, it has to be subtracted. So whenever the signal stops, it has to be negated. And now we will look at t minus 2. So now notice the signal of t minus 2 starts at t equals 2, so I'll attach a u2 to it. It will be positive because that's where it begins, and notice it never ends. And because it never ends, we will not have to subtract anything at all. And now we may simplify this. So therefore, f of t is simply t minus 2 u2. And now we may attempt to take the Laplace transform of f of t. Now from a list of Laplace transforms, you may notice that the Laplace transform of f of tau u alpha is equal to capital F of s e to the negative alpha s, where tau is t minus alpha. So in our case, alpha is 2 because we have a unit step function u2. And therefore we are going to make a substitution that tau is t minus 2. Well, if tau is t minus 2, then f of t becomes tau u2. Because I can replace this t minus 2 with the tau. And therefore, if I want to take the Laplace transform of f of t, that is the same as taking the Laplace transform of tau u2. And for the Laplace transform of tau, that is what we are going to call f of s. So f of s is basically the Laplace transform of tau, which from the table or a list of transforms can be evaluated as 1 over s square. And therefore, this becomes 1 over s square. And because of the u2, we have this exponential term e to the negative 2s. And therefore, the Laplace transform of t minus 2 u2 is 1 over s square e to the negative 2s.